Hello, it's What the Doodle here, and in today's session it's going to be an update of the RDFS, which is the Rust distribution file system, and that project essentially is a toy implementation of the Google file system. So this is the actual repo itself, and in the previous videos, so if you were to watch the previous videos on this topic, in the previous one we originally talked about because the actual RDFS has three main parts to it essentially. There's the worker node, there's the master node, and then the client node. So in the previous video we looked at the development of the worker node, which has been completed, and since then a lot more development has been done, and the focus of today's video and update will be essentially the master node. The master node is not complete because it is a lot more complex. In terms of the complexity, the worker node is the least complex. The master node is a little bit more complicated, and the client is also, there is some complexity there. And so in the master node at the moment, where it stands, it is about 80% complete. So we don't need that particular tab. I'll close that. So if I just dive straight into the code, I can show that. So as I mentioned, most of the focus has been on the actual master node itself, and there's been quite a lot of stuff that has gone on in terms of the actual implementation. And I took a little bit of a break in the sense that the way that I approach to system design is I do a lot of it in my head actually. So I will tend to think about the overall project sometimes, and of course sometimes that design can get quite granular, but a lot of that design actually happens in my head. And once I am pretty confident about the design and I think it will work, I then actually go to actually implement that, because I then have a direction. And actually what we can do is, I am in the RDFS repo, and this is the most latest commit. So let's try and build that. And what I tend to do is, when any work that I have, whatever I commit and push up, I always like to have it at least buildable. So even if there are features or things that are incomplete, or there could even be bugs, I tend not to push that to GitHub until it's at least compiling. And in this version, there's been a few new dependencies that have been added. And also this reminds me, actually, there was actually a contribution by a GitHub user. I think the username was Robert. So thank you, a shout out to Robert for making that contribution. I believe he added he enhanced the actual logging using things like the tracing crate or something like that. And it adds a nice little touch, because I was just doing raw print line essentially. So I wasn't even bothering doing any kind of logging or anything like that. It just adds a nice little touch. So once again, thanks for that contribution. And that is what actually one of the brilliant things about open source is the fact that it's completely open, and it's complete free collaboration. Anyone can jump in and help out, or even play around with it. And really, that's the whole point of this particular project anyway. It's just it is, the whole thing is a learning project really. So feel free to contribute. And obviously it's still in flux, of course, and a lot of things are changing, but of course one of the largest, more complex chunk is the master, which is, as I mentioned earlier, 80% complete. After that will be the client, and that really would wrap up the whole project. Once the client node is completed, that would be the entire RDFS project. And I think it's a fairly nice self-contained project that certainly could be expanded on and played around, and a really good sort of learning aid. Right, anyway, so if I source the environment file, I can actually show you that little minor change that was added in. So when you run it now, you have proper full-on logging on here. So you have these nice logging things in here, which is pretty decent. Okay, so if we go to the actual code itself, so as I mentioned, it took a long time to think about how to design it, how to approach it, because the master node is essentially a metastore database. It's the thing that stores information, or meta information about all of the files that are distributed across the cluster. And so I had to think about how best to approach that, in terms of storing that data. And of course, we're going to store it in memory. And so this is what I came up with, is essentially a struct called Metastore, and it has the following things: it has file name, hash, chunk ID, and host. I'll go through this. So obviously, file name is pretty straightforward. A particular file will have a file name, and the hash is the content hash. So once you take that particular file and then you hash it, the actual content itself, you will get you'll get a cryptographic hash. Now the cool thing about that is that hash will always be the same for the same exact content. And that's kind of cool, because then you actually get a free bit of optimization, because, for example, you could have different file name could change potentially, but if the content is identical, then the hash will actually be exactly the same. And so really the file names then become essentially aliases. And that means you don't have to have a data duplicated in terms of in the cluster. You don't have to store that hash again, if that makes sense, because, as I said, the hash is unique based on the content. So you effectively get deduplication for free. Now we have two parts to that. We have the hash and we have the chunk ID, because if you remember, we take a file and we split it into chunks, and so a single file will be split up into multiple chunks. The hash will remain the same, but what we do is we create what is called essentially a composite key. And that composite key is made up of the hash and the chunk ID. And the easiest way to think of it is fairly straightforward. You can, if you split a file, say as an example, into 4 chunks, so you'd have essentially one chunk ID 1, 2, 3, 4, and the hash would be the same. Let's say the hash is ABC, so we would format that as, for example, chunk ID 1 would be 1 dash and then the hash, and then the second chunk would be 2 dash and then the hash, and so forth. And you'll see why that's quite helpful later on in the code. And we also need, of course, a list of the hosts. So the hosts are where the actual worker nodes, and the hosts themselves. We have a struct to define the host, which is simply just the IP address and a status for that host. So the status is pretty simple. It starts off as unknown, and if we get something back, if we get a heartbeat back from that particular host worker node, we mark that as healthy. Of course, if it's past a certain fixed timeout, we can then mark that as dead. So really, those are the only 3 try states for now, anyway. And as I mentioned, it essentially is like a global variable. So here we use this lazy static because we need to initialize it, but we kind of want to do a late initialization, because we just kind of we have this in memory essentially. And so we use this cool lazy static crate to do that for us. And as I mentioned, it is kind of like a global variable in the sense but we essentially use these mutex guards, which is a mutually exclusive guard that allows us to be able to access that same piece of data, if you like, in a thread safe way. Because of course, if you have multiple threads, because this is a multi-threaded application, we don't want to have this issue where different threads kind of try to write and mutate that same piece of data. You will get into issues. But with the mutex guard, thankfully the type system helps us, because you essentially, what you have is that you essentially put a lock around that. So whichever specific thread is trying to access that data puts a lock around it, and then does the mutation. Once it releases the lock, another thread can then safely access that, or it'll wait. So another thread will wait until that lock is finished. So yes, there can be certain performance implications because of locking, but then whichever multi-threaded application you look at some level you have to do some amount of locking. I mean, there are these other sort of they call them lock-free algorithms, but at the end of the day, if there is 2 things trying to access one thing, somewhere at some point something will have to wait. And anyway, so that is the we have the meta state, which is one global, and we have the heartbeat, which is related to the worker nodes. When they send in heartbeats, we need to capture that information as well. Now, one of the issues is this is all fine. So we have the metastore all in memory, and it gets populated and it gets mutated and whatnot. That is all fine. However, the issue is once this master node process ends, then all of that stuff, all of that data in memory will disappear, and that would be catastrophic because the metastore, which is the index for all of the files for the entire cluster, if that disappears, you effectively lose your data. Now, you don't physically lose the data because all that data is still available on all distributed across all of the cluster, all of the worker nodes. However, if you don't have the metastore, which is the index, then you really don't know because it's completely, not random, but the chunks will be completely split up. So a file will be split into chunks and then distributed randomly across the cluster, and so you would not know how to stitch it up because this is the metastore that holds that information. It's the thing that says, okay, for a given file, these are the chunks, and these are the places where you can find those chunks. And so for that reason, what we do is essentially to solve that problem. What we do is we essentially keep a log, an event log, which is saved to disk. So as each of these mutation for this metastore, as this metastore data, as that mutates, every single time it mutates, we save it as an event in a file, and so that's brilliant. So we'll have a series of events on disk. So it's essentially a log, and what we then do is when the process, so if the process then crashes, when the process reboots, and that log, by the way, I call it a snapshot. So when the process reboots up again, what we do is we load those events and we reconstruct essentially the in-memory data. And one of the things we have to do is compaction, because if you imagine the same element, so this metastore is a list of metastores. So if you imagine one particular metastore or one particular file, let's call it file bob.txt, and over time you have multiple events where bob.txt has changed, for example, the hosts have changed around, then each of those, so it would be a single, it is a single record, but it would be a record of events that changes over time. And so with compaction, what we do is we replay those events until we get to the very last event. So and then we can remove the other ones, because the latest events, if you play all the events in order right to the end of that log, eventually, and you load it into memory, you will have reconstructed what the memory was before the process shut down or was ended. So that is what we use. That's what we do with the snapshot. We do that compaction, as I mentioned, and then what we do is after we load everything, after we reconstruct. So if I actually go here to the actual function that does this, so not the upload, not here. So load snapshot. So as soon as the process boots up, the very first thing we do when we initialize this is we load the snapshot. And as I was mentioning, what we do is that we load it from disk. We load all of those events, those metastore events. And as you can see, we use this. I've called this a compactor. And essentially all it is a hash map, because I found this is a very sort of a simplistic way to do the compaction. There was lots of different ways of kind of approaching this, but I found this to be the sort of the easiest way to do it. And what we do is we have as I mentioned, that composite key, which is made up of the file name and the chunk ID. So that is the composite key. That's the unique key, if you like, for that particular metastore record. And what we then do is we essentially, you can see that entry here, we have the hash and we have the chunk ID. And what we do is we essentially, if it's the first time that thing, that it's the first time that key exists, or so it doesn't exist, then we insert it, we do an insert. If it does already exist, we actually modify it. So we're constantly overwriting. Now, that's maybe not the most efficient way to do it, but it's certainly the way that I found it the easiest way to do that, using this compactor, which is a hash map. And then eventually we turn that back into a vector, basically in memory, a vector in memory, which is just a list-like structure. And the other thing we also do, so that helps us deal with all of the mutation, but we also have to deal with deletions. Now, deletions is kind of different, because if you imagine the same record has been mutated, it doesn't matter 5 times, 10 times, or however many times. If at some point it has been deleted, or if it's been deleted, then the entire history of that record, all those events are irrelevant because it doesn't exist. It's been deleted, and so in order to deal with that, we have a separate file. We save the delete all of the deletion events, all of the hash that are deleted in a prune file. Essentially, we call it a prune file on disk. So what we do then is, as you can see here, what we do is we check to see, whilst we're loading up this from all these events, these snapshots from disk, while we're loading that up, we also check to make sure that it's not in the prune list. Because it means if it's in the prune list, it means it's been deleted, and we can safely literally just skip all of those events. There's no point dealing with that because it's not going to exist. So essentially, anything that's in the prune list will not be loaded back into memory. So it's the same as deleting it, and not just it, but all of the history. So with the combination of pruning, so we do pruning is kind of the pre-process step. So it's not a pre-process step. It actually is kind of combined and merged into one. But it has the effect of pre-pruning, which is removing those dead records essentially, and compaction, which is to combine all of the various different events into a single final event. And then what we then do is we then write, once we've loaded all that, we export that compacted snapshot, which is to say we write that snapshot back to disk. And the reason we do that is because we could skip this, but then it would mean that the next time when it loads it'd go through all of this again. It would recompact stuff it's already compacted. So by exporting that snapshot after it has been pruned and compacted, you have a much more compacted version, snapshot if you like, which we can then, because as the process then carries on, as the master process carries on and the mutation events happen, they get appended. Those events gets appended to these snapshots, to the snapshot file essentially. So that's how that happens and all of that works. So this is to do with all of the compaction and the snapshot and the pruning, and of course we need to do that. That's part of the initialization, and by doing this we now have, we don't rely on any databases or anything like that, and it's all self-contained, and all we're really doing is it's also safe in the sense that we will, if the master node is shut down, we do not lose the Metastore, because we're persisting that information to disk, and we're reloading it back into memory. Okay, so that's all fine. So that's all working, and so if we go to the actual, the minimal amount of things that we need to do. So of course we have the heartbeat. So if we look at the heartbeat, and incidentally, the heartbeat uses a similar trick to how we did the compactor. Essentially, we take the IP address as the key, because the hash map will use the IP address of the worker node as the key, and then we essentially just, if that's the first time it has been added to the hash map, then we just insert the timestamp, which is the instantaneous moment right now at that point when it was called, or we modify it if it already exists. So it will be constantly overwriting. So each time the heartbeat goes through, essentially it will have the last time the heartbeat came from that particular worker node. And so that is literally just a heartbeat. So that's pretty easy, pretty straightforward. And then we have the list. So the list command is when we need to see all of the files, that just the list of all the files that are in the Metastore. And the list, if we go down here, list is pretty straightforward, and it's one thing I do like. And you can see, of course, here's the locking mechanism of the mutex, which is pretty handy. And I mean, the list is pretty easy actually, because we just essentially we iterate, we do a map, and this is one thing I like about. Well, there's lots of things I like about Rust, but this is all very sort of functional programming style-esque. You don't need to, it's more declarative-ish. I mean, I don't say it's completely declarative, but it's similar to those things that you do in other high-level languages like C# or like LINQ and all those other things, and in Java, and you have things like streams, and in Kotlin you have all of the, the classical things that you do manipulation on lists and things like that. Of course, it's not purely functional like Haskell or anything like that, but it's still just enough functional to make life a little bit easier. So there's some nice creature comforts there, and so essentially we just iterate through that in memory vector, and we map it. We just pull out the file name. Essentially, we then do effect the hash makes it sort of unique. So we deduplicate, remove any because we will have a lot of duplicates, because if you remember, the actual metastate is for every single hash, and we don't, so every single hash chunk. So if a file has 50 chunks, then there'll be 50 entries for that particular file, and of course we don't want to repeat it 50 times. We just want this, just a distinct, essentially. It's kind of like doing select distinct from in Haskell, in SQL, but we're doing all of this in memory, so there is no SQL. And then finally, once we have all of that, if there are some files after all of that, we serialize it into JSON and send that back. Otherwise, we error out. So that is the list, and that's actually one of the more easier handlers to do. And then when we want to do the get, which is to get a specific file, again, very simplistic. We do a filter this time, and we don't we just filter by we filter by the file name, essentially. And so this will pull back a list of every single Metastore, which is a list of every single chunk, which is that structure that holds. And then later on, of course, the client will need to pass that, so you'll need to deserialize that, and you'll need to figure out where it will have the meta information about where the worker nodes are for each of those chunks, and it can pull those chunks down in parallel and then reconstitute it and stitch it all back together. So there's a lot more work that has to be done on the client side, but from the master node side is pretty straightforward. Well, certainly those two handlers are. Now, I'll come back to this in a second, because this is, as I mentioned, 80% has been completed, but one of the main one, which is the upload functionality, has not been completed. I will talk about that a little bit more in detail. The remove, of course, is fairly straightforward. Well, not straightforward. It's you essentially remove it from memory, and then what we do is we have to build up a kill list, essentially. So those chunks, they have to be removed from memory. They have to be also appended to the prune list, which is or the prune file, which of course we mentioned earlier on how when the process is booted up again, it has to use a combination of the snapshot and the prune file in order to remove dead elements. So it doesn't come back into memory. It's not loaded back again. But we also at the same time, what we do is we have to call the remote, which is essentially the worker node. We need to actually tell them to remove that particular chunk. And if you remember, on the worker node, there was a few different handlers. So we had get chunk, store chunk, delete chunk. So it calls the delete chunk. So the master calls each of the workers that has the chunks distributed, and it calls the delete chunk method in order to delete that. So that's that part of it. Actually, I haven't finished that, but that's just an API call. So that's pretty straightforward to do that. So now if we go back to, if we have a look at this, and so I'm just going to go look at the different ones. So heartbeat is implemented, list is implemented, get is implemented, remove is, let me just check, I believe, hang on. So upload and apologies. So remove has been implemented. So this has been implemented. So the only function, this is why I mentioned that 80% of this project, of the master node, apologies, is completed, is the upload. So the upload is the only bit that I have not completed yet, and I've left a big chunky note to myself, because there's a lot of things involved in the upload part of it, because We don't actually upload, if that makes sense, because the upload happens by the client. What we do instead is, I mean, if I just summarize all of it, because there's quite a lot of notes here, you can go to the repo and read it. I'm not going to reread that. So if you go to the GitHub repo at What the Doodle, you can have a look at that. But essentially, what needs to happen is we need to, when a file is requested to be uploaded, we need to sort of we don't do the splitting. We have the meta information about how to split it, and we also need to take into consideration at that moment in time all of the live nodes, and also we have to think about how to sort of distribute it so it meets that replication factor. So the replication factor is met, and and then we send that information back. But of course there are failure modes as well, and that's why it gets a little bit more you have to think about how are you going to address the retry mechanism. And for example, what you could do is you could recompute. So when essentially this is a big fat computation that needs to happen, where it computes the live heartbeat in terms of what exists in terms of the worker nodes, and it has to sort of figure out how to, in terms of that file split, and where to distribute them. So those things have to happen. And of course, as I said, in terms of the retrying, what it could do, you could take one naive approach. So this is, imagine where the upload function has been called and it's done its computation. It said, place these chunks at these various different worker nodes, and it sent that information back to the client, and the client has tried to do that and failed for whatever reason. Maybe maybe a worker node is dead or something, I don't know, but for whatever reason, network issues or any number of reasons, it failed to finish that. As far as this is as far as the meta or the metastore information is concerned, because after it sends that information to the client, it just assumes it's completed. So it makes a very naive assumption that the client is always going to complete successfully, but that is not, of course, the case, because lots of things can fail. So the retry, if it tries to send it, what we can do initially is just to recompute everything, and that's fine, because oftentimes you'll have two cases. The chunks, when they are recomputed, it could be that the chunk already exists, and that doesn't matter, because if the chunk already exists, I don't know if I've done a bit of check where if the chunk already exists, whether if you re-upload the chunk with the same chunk, I think it most probably would just overwrite it. But in any case, the danger is that whilst there will be overlap when it does the recomputation about where to place the chunks, it could be that it picks a different server than originally when it recomputes it. And in that case, what would happen is that you'd end up with a dangling chunk. So you'd essentially, and that chunk, that it means that will be a chunk that exists on the worker node that, as far as the metastore is concerned, shouldn't be there. And we call that essentially dangling, orphaned. There's multiple ways of calling the same thing, but it's not the end of the world. However, over time, all of those orphaned chunks would essentially waste a lot of disk and take up a lot of it would essentially leak storage in that sense, because it's taking up storage that it shouldn't do on the worker nodes. So of course, in order to solve that problem, we would have to think about some form of garbage collection. So this would be something that periodically runs on the worker nodes, and where thereby the worker nodes makes a call into the master based on the chunks that it has, and then it can pull down some information to confirm whether it really should have that chunk or not. So, and we'd have to think about how to do that in a very efficient way, because obviously, if you imagine, a worker node's got millions of chunks, and then you have 100 worker nodes, each of them having millions and millions of, you can see how that could be quite intensive. So of course, the garbage collection would not run all the time. It would run when the worker node is idle, at some time, and they would be spaced out essentially. But still, we would need a way to think about how to approach that design so it is implemented in an efficient manner, so that we minimize the amount of data that is exchanged and also that we minimized mostly the network calls. So how many few network calls can we make essentially in order for a worker node to determine if the chunks that they have should exist, and if it doesn't, it's basically to identify an orphan chunk essentially, and then once it identifies that, it can remove that cleanly. So and of course there's the other things about how do we handle rebalancing when a particular node goes offline, and things like that. So yes, so that's why this is the upload functionality is the most it's one of the more complex part of this project. But anyway, it's getting there. It is getting there, and hopefully once this part is done, I will then move my focus towards looking at the so of course, as I mentioned, the worker node is done 100%. This is 80-90%. Just that upload functionality has to be implemented. But I said there's a lot of little details that need to be figured out. And then once that's done, I can then look at the client. And client really ties all of it together, because this is the one that speaks both to the master, but also has to directly contact each of the workers, both in terms of when it has to pull a file. So when it gets a file, it will talk to the master. The master will provide it meta information about where everything is, or because it's distributed across the worker nodes. It would then go to each individual worker nodes independently and pull the files, and then reconstitute that file, and you have that file. And it also works in the reverse, where when it wants to upload a file, it would send a request to the master. The master will decide where in terms of the placement for all of the different chunks. And once it's done that calculation, which is the bit I just showed, which has not been implemented, it would then send that information back, and then the client will then chop up the file into chunks, and then based on the Metastore data that it has, based on the calculation that the master has done, it would then directly send it. It doesn't need to send it to the master, so it would use the store chunk API of each of these workers that we have. And of course the same in terms of deletion and in terms of listing, which are a little bit easier because it doesn't have to really interact with that. It's more so listing and removing removing essentially is to, it would send, as you've seen in that handler, it already has all that information in terms of Metastore. Client does not need to know that, and based on its internal understanding of where the distributed chunks are, it can go ahead and issue the delete chunk into each of those worker nodes. And in terms of listing and getting the file, that's just a read-only action really. That is whatever's in memory, just chucks it back at the client. Obviously serialized as JSON over the wire. But so that is where we are at the moment with this project, and I am still pretty excited, and I think the biggest excitement will be once the client part of it is finished, because then, as I said, that would be the complete project, and it would be very, very interesting to see how it behaves, because then we would have essentially a toy. It's quite amazing. We will have a toy distributed file system. It's somewhat like the Google file system, or based or inspired, you could say, at least inspired by it, but also completely done, obviously in Rust. But the nicety is the fact that it is a polymorphic binary, just a single binary, no other dependencies, and you can just throw this on multiple servers, and it will form a cluster, and we have essentially, it doesn't have all the features of a full fat production grade distributed file system like Google GFS or RDFS or even S3. However, it is still, at least it would be a workable one, a toy version of it. Now, of course, going from there, obviously fantastic for people it would be brilliant if people are interested in this kind of thing to tinker around with it, and also in terms of like not just to tinker around with it, but just have the ability to play around and just see, okay, how could this be improved? Where could we add performances? What other features could we start adding in? And it's just completely, because it's because it's written from the ground up from scratch, and it's not it's not the existing like S3 and HDFS and a GFS Google file system. It doesn't. It's not restricted in terms of, in the sense that those are existing production systems, and they already have a set of features, and they're near impossible to change because it's a real world production business critical system, and you can't just go in there and make dramatic radical changes, because it's too important, too many businesses attached to the back of it. However, with something like this is a complete toy implementation, and it's completely for educational purposes, and it's not production at all, so you could go absolutely crazy and try all sorts of things. Like, for example, I'm really interested in things like WASM as a plugin function. So that could be quite cool, is to have like a plugin based system for this distributed file system, where you could essentially, on the master, you could load up plugins to do all sorts of things. I don't know, maybe you could do things like file encryption and so many kinds of things. There could be like data redaction, and maybe all kinds of things. They're that you could do with data essentially, but they could be done using plugins. So that could make the way that plugin could work, as I said, as I mentioned, in terms of the fact that you have this polymorphic binary that you can just throw on any server, and it all forms a cluster. In the same way, it would be brilliant to have like WASM plugins where you just drop the WASM files right next to the master binary, and the binary will be like, oh, I've got a new plugin, and then it could load up that plugin and then apply it. So it's like a really kind of cool approach. Right, so that is where this project update is for the master, and hopefully I can complete the last bit of it, and then start tackling the juicy client bit of it, which will really tie the whole thing together. So yes, until next time, I will see you on the next one.